Hello everybody, this is Dr. C. Hopefully a really short pre-lecture for today. This one is just going to focus on one section of the textbook. I believe it's 15.10, looking at the structure and predicting acid strength. So far we've looked at strong acids and weak acids, and we identified the 6 common strong acids and so on, but we didn't talk about why one acid is stronger than another, other than to kind of memorize it. So let's finally actually look at the structure of the acid and how that impacts strength. Now there's 2 things that we do have to consider. 2 factors. One is bond strength and the other is bond polarity. So you should remember these 2 concepts from Chem 151. Bond strength, we talk about a bond energy or bond enthalpy. It's the energy required to break a bond. Okay, and then there's bond polarity, and that's an electronegativity difference. Electronegativity, EN for short, electronegativity difference. The larger that difference, the more polar the bond. And you might remember that fluorine is the most electronegative element. Okay, so this is kind of all review. So for binary acids, and these are kind of the simplest acids. Binary acids, they only have, and here's some examples, hydrogen and one other element. Okay, hydrogen and one other element. So things like hydrofluoric, hydrochloric, hydrobromic. Now, when they're in a group, okay, or what we also call a family, a column of the table, bond strength is the determining factor. And I'm trying to flip through my book back to chapter 9 right now as I'm doing this. I should have done this beforehand to look at some bond energies just to give you an example. And I'm almost there, I hope. Chapter 9, here we go. So if we look at these bond energies, HF, bond energy is 565 kilojoules. That's for HF. Let me just write them on the side. HCl, see if I can find it. Oh, it's not going to make my life easy. 431 kilojoules per mole. Okay, HF was 565. HBr is 364. And HI, it's 297. Okay, so you can see that as we go down the family, the bond gets considerably weaker. You know, an HI bond is about half the strength as an HF bond. Okay, and that's partly, mainly because hydrogen is a really tiny atom, and fluorine's pretty small, so the orbital overlap's going to be pretty good. But when we try to bond hydrogen to larger atoms like chlorine, bromine, and iodine, the overlap of orbitals is not going to be very good, and the bond's going to be weaker. So in this case, the bond becomes weaker. And what do you notice about the acid strength? Weaker bond, stronger acid. Okay? It's much easier to break this HI bond, which is what we need to do to donate an H+. When we break this bond, the electrons are actually going to come up on iodine, and we're going to lose an H+. Much easier to break that bond and donate the H+ than for HF. Okay? And as you might remember, HF is a weak acid. All these other ones are strong acids. But of the 3, HCl, HBr, and HI, HI is the strongest acid. Weakest bond, strongest acid of that group. Now, what about if we go across a row, or what we also call a period? Well, bond polarity is the greater determining factor. Okay? And again, fluorine is the most electronegative, so electronegativity is going to increase across. So we have nitrogen, oxygen, fluorine. Okay? So this bond is the most polar. OH bond is pretty darn polar in water, but it's not as polar. And even NH3, an NH bond, while polar, is going to be less. Okay? Now, in this case, the greatest determining factor is polarity. The more this looks like an H+, okay, the more polar that bond, HF is the most polar bond of that group, okay, the more that hydrogen looks like an H plus. And I somehow did not, the I did not show up. Looks like an H plus. Okay? So again, polarity, charge separation. Fluorine builds up a partial negative charge. Hydrogen builds up a partial positive. That's the most polar, so hydrogen is most like an H plus, and it's more readily donated as an H plus. Okay? So polarity increases this way. Okay? And acid strength increases as well as we go across a row. Okay? As we go to the right. Okay? And we know HF is a weak acid. Water can be an acid or base depending on what we put in it, but if we put HF in it, certainly water would function as the base, not the acid. So that's certainly weaker than HF. And ammonia we tend to think of as a base because water is stronger as an acid. So we dissolve ammonia in water. Water will be the acid, it's stronger. Ammonia will function as the base. Okay, so if you want to read a section of the text, read section 15.10. And let me just flip to that real quick. Let's see if there's any example problems there that you should take a look at. Let's see. There is a conceptual exercise, 15.6, and that's about it. So there's not really any example problems, but it's only a 2-page section. I would read it, work the conceptual problem there. This is a fairly easy concept, although the rules for binary acids going down a column and across a row are different. Down a column is bond strength, across a row is bond polarity. Okay, other type of acid, oxoacids. They contain hydrogen, oxygen, oxoacid, or also called oxyacids, and a third element. In this case, it's nitrogen. So a hydrogen, oxygen, and a third element. This one's all about polarity because they all donate the hydrogen ion from the same type of bond. And it might seem kind of odd. It's actually from an OH bond. And we think, OH, isn't that a base? No, we're donating an H+. We're breaking that bond. Electrons come up onto oxygen. We lose hydrogen as an H+. That's an acid. Okay? So the more electronegative groups you have, and oxygen is highly electronegative, the stronger the acid because it pulls electron density away from the bond, making it more polar. So for example, okay, there's nitric acid. I haven't completed the Lewis structure for that, okay, but let's just leave it at that. This oxygen, each of these oxygens is going to pull electron density toward itself, partial negative, partial negative. Okay, that will kind of create a partial positive on nitrogen, but nitrogen's a highly electronegative element, so it's going to say, well, I'm going to try to steal some electrons from oxygen over here, even though oxygen doesn't want it, and then oxygen's going to steal from hydrogen, and that will make this bond more polar, more like an H+, easier to donate as an H+. So nitric acid, HNO3, has more electronegative oxygens, makes that OH bond more polar. This is more like an H+, and is more readily donated as a hydrogen ion. Okay? HNO2, on the other hand, only has one oxygen pulling electron density away. So this bond will certainly be polar, but it won't be as polar. Okay? And so our goal with polarity is to try to make that bond the most polar. Hydrogen, most like an H+, it's more readily donated as an H+. So we know HNO3 as a strong acid. HNO2, on the other hand, is a weak acid. So there's your difference in acid strength. Just to show you some other examples of oxoacids, carbonic acid. This is a diprotic acid. It has 2 hydrogens it can donate. We looked at nitrous HNO2, nitric HNO3. Here's phosphorus and phosphoric diprotic and triprotic. So phosphoric acid has 3 OH bonds. Each of these hydrogens can be donated. Okay? So those are oxoacids. And just one last thing for this pre-lecture. Let me show you one more thing. Let's say we have this. And the same rules, let's use fluorine. Let's make this an F. So this is a carboxylic acid. Here is our COOH group. This is actually called trifluoroacetic acid. Okay, 3 fluorines, and this looks like acetic acid, so let's compare it to acetic acid, which instead of fluorines would have hydrogens. Now, I'd like you to pause this video and think for a second. Which of these do you think would be the stronger acid? Now again, we need to, the hydrogen that will be donated will be from the OH bond of that carboxylic acid. Which of these do you think will be the stronger acid? Pause for a second, think about it, and make your prediction. All right, so it's the same thing. It's about polarity. Which of these will have the most polar OH bond? And again, it comes down to the electronegativity of the surrounding groups. Fluorine is the most electronegative element. It's going to pull electron density away from carbon. Carbon will try to retaliate on that carbon. And we kind of get this effect where all the electron density is trying to get pulled toward the fluorines. It makes this bond more polar. Okay? A carbon-hydrogen bond is essentially nonpolar. Their electronegativities are very close. So that's not going to have any electron pulling away. This will still be a polar bond, but just not as polar. So electronegative groups pulls electron density away from this OH bond, making it more polar. Hence, this is more like an H+, stronger acid. All right, that's it. Section 15.10. We'll also talk about in class, we'll talk about Lewis acids and bases, which we really have already done. Remember when we talked about, rather than talking about H+, donor and acceptor, we talked about looking at electrons moving, donating electrons and accepting electrons. We'll look at that again just to refresh, but that's called a Lewis acid and base definition versus Bronsted acid and base. Okay, that's it for today. See you soon.